Hello friends, my name is Chinmay Deshpande. In this video lecture, we are going to discuss about a topic from economic load dispatch. The topic is economic load scheduling with transmission loss. Now the transmission losses are negligible if a high density load, that is urban or industrial load, is separated by a small length of a transmission network. But if the load is of low density and it is separated by a long transmission network, that is a rural load, then the transmission losses can't be neglected as they are about 20 to 30% of a total received power. The necessity of inclusion of transmission losses in an economic load scheduling can be explained by a system. Let's say I'll take this system as, let's say this is your generator G1. This will be your generator G1. This is your generator G1 bus. This will be your generator G2. So this is your G2. And here, suppose let's say a load is connected at this bus. Now, let us assume that there are two generators having exactly similar incremental cost curve. Since both the generators are similar, each of generator should supply half of the total load for economic load scheduling whenever transmission losses are neglected. When we haven't considered transmission losses, if it is not equal to or if it is equal to 0 and the incremental cost of both the generators are same, then I can say that suppose load is 100 megawatt. So generator G1 should produce exactly half, that is 50 megawatt. Generator G2 should produce a 50 megawatt. It's okay. But from the figure it is clear that generator G2 supplies a load without any transmission losses, or we can say whatever will be the transmission loss associated with this bus, it will be 0. But if you take it from the power from generator G1 to this load, then it supplies the load with a certain transmission loss. Therefore, economy suggests that G2 should supply maximum of a load and G1 should supply minimum of a load. Therefore, it is necessary to consider the transmission losses for economic load scheduling. So let us consider that here N will be equal to number of generators. What is this N? Number of generators, or in other words you can say these are number of plants, N number of plants. Then let's see, PD will be equal to a total power which is to be demanded, or I can write total demanded power. Then this PL, let me take this PL, is nothing but what? It is transmission loss power. This is total transmission loss power. Now, as we discussed earlier, what is C1, C2 up to Cn? This is nothing but cost of a generation by unit 1, 2 up to n. Cost of a generation by unit 1, 2 up to n. So we know that total cost of generation will be equal to what? C1 plus C2 up to Cn. In other words, I can write it as Ct will be equal to summation I equal to 1 to n Ci. Let me take this as an equation number 1, where this Ct is nothing but what? It is nothing but your total cost of generation. And let me write it as, let's say Pg1, Pg2 up to suppose Pgn. What is this? This will be your power generated, or output power generated by generator G1, generator G2 up to, let's say, up to generator Gn. And already we have gone through this. PL is nothing but this will be your total loss power. This will be your total loss power. Now what is our aim? As we discussed earlier in our Lagrange's multiplier method, same we will write it here. What is our aim? To minimize the CT, that is the total cost of generation. Now here we have to take again equality constraint. Here we have to take again equality constraint to minimize the cost of a generation CT, so that Now I have some kind of demand. Okay, that much amount of generation should be there, so I will write it as I equal to 1 to n. This was the earlier case when we haven't taken into consideration the power loss, but here now we have to take a power loss. So PD plus PL equal to summation I equal to 1 to n PGI. Now why we have written like this? Because we know that generation should be like this, whatever demand and whatever power losses. Okay, beyond that some kind of generation has to be there. So here from this, from equality constraint, I will write this expression as PD plus PL minus summation I equal to 1 to n PGI, which will be equal to 0. I will mark this as a equation number 2, and we know that this will be what? This will be your equality constraint. But what kind of equality constraint it is? It is equality constraint when we are not when we are taking into consideration the power loss. Now, as we know that what is this Lagrange's multiplier method equation? We know from a Lagrange's multiplier method, C will be equal to Ct plus lambda into F. So let me take this as a equation number 3, where Ct is the total cost of generation, lambda is a Lagrange's multiplier, and this will be equal to your F. So how I can write? PD plus PL minus summation I equal to 1 to n PGI. Okay. Now we know that if I want to minimize the total cost of generation, so I will write it as minimize total cost of generation. So we know delta C upon delta PGI will be equal to 0. So therefore from this expression I can write it as delta C upon delta PGI will be equal to delta Ct upon delta PGI plus lambda. Okay, let me write it as delta upon delta PGI into bracket lambda of PD plus PL minus summation of I equal to 1 to n into PGI. Let me take this as bracket complete. And we know that it should be equal to 0, so that's why we will take it as equal to 0. So how we can write? Now can I write like this, delta Ct upon delta PGI, which will be equal to what? Delta upon delta PGI. Already we have seen this, summation I equal to 1 to n PGI. Remaining thing will be as it is, delta upon delta PGI, and whatever will be the equations here in a curly bracket, we will write it as it is. So therefore how I can write? Now from the right hand side, whatever we have a right hand side, from that can I write like this? How I can write? It will be equal to dCi upon dPGI. dCi upon dPGI plus lambda into bracket. As PD is a constant, so with respect to derivative of PD with respect to PGI is 0. But PL is not constant. Please remember, that depends upon your, what we can say here, that depends upon with respect to which generator we are taking. For this generator, the power loss is minimum. For this generator, power loss is maximum. So with respect to generation, it is not a constant. So what we have to write is, we have to write it as plus delta PL upon delta PGI minus 1, because derivative of this with respect to PGI, it will be equal to 1, which is equal to 0. So can I write from this? How I can write the expression? It will be what? dCi upon dPGI will be equal to, now I have to multiply this lambda, so lambda delta PL. Okay, let me write it as lambda delta PL upon delta PGI minus lambda. So I will shift this term towards right hand side. So it will be what? Lambda into bracket 1 minus delta PL upon delta PGI. Please remember this expression. This is very important expression. This is nothing but your coordination equation. This is nothing but what? Coordination equation. Earlier when we haven't taken PL, then it was what? dCi upon dPGI equal to lambda. But now here we are taking this what we can say a power loss. So that's why what this will be called as, this is your coordination equation. Now, therefore, please remember, it is to be noted that for solving a coordination equation, when this power loss has been considered, then it is necessary to find it out DABA PL upon DABA PGI. It is required in this formula. We need to find it out transmission loss PL in terms of plant generations, DABA PL upon DABA PGI. So this is what is, we can say, coordination equation of economic load dispatch when power angle has been taken into consideration. So this is a total derivation for this topic. Thank you for watching this video. If you have any doubt, please feel free to ask any questions. Thank you once again.